view of what we're going to need, which I'm going to do right now. So, things that you're going to need to know right off the bat. So you need to know the definition of the derivative, right? So what is the definition of the derivative? Okay, well that's a graphical definition, but like in terms of the formal definition, it is if I have you better. So if I have, let's say, some function f of x, right? I want to know what its slope is or what df dx is. And it's defined as some limit as delta x goes to 0 of the difference function. I'm pretty sure everybody here has done this on some level with pre-calc, right? At the end of pre-calc, you touch this. You might be doing this in calc this year. Now, Jonah, you're able to do the calc stuff based on the videos? All right, cool. So, now how were the videos? How were the quality of them overall?
I thought they were pretty good.
Yeah.
They cut off like this bottom half.
No, you just go to YouTube.
Yeah, I just opened a link, but I kept
Yeah.
the haiku link running because I didn't know if it would count or not.
So this should give you guys, all of you guys, this should give you a really good backup for your calc classes too. Like if you're taking AP Calc and you miss, let's say, a couple days, just go onto my haiku page and you should basically get the equivalent. So,
Is IB or AP Calc?
I mean, they're all the same. They're all the same.
In my class, there's IB, like Math, HL, and APC Calc. It's like the same class now.
Okay.
She was like, oh, like whoever's taking AP might go switching to a different class or something. But there's only one other person.
I mean, honestly, you want, like, and you, in particular you want to go well beyond the AP curriculum and the HL curriculum. You want to go way beyond it. And I have ideas as to what you should do in terms of, well, no, it's more like actually going in, looking at sequences, understanding how continuity relates to sequences of functions, and so on and so forth. Because you're going to need that in physics. If you're going to be a physics major, you're going to absolutely need it for quantum mechanics. Because in quantum mechanics, you really stop getting the smooth. You can easily stop getting the smooth class of functions which categorize everything we're pretty much going to be learning. So, and it's good to actually really analyze the real number line. Anyhow, that's a separate story. So, so things that you're going to need to know. If you have, let's say, I'm going to give you a whole class of different functions. Let me drop this down to 150. So if I have f1 of x equal x to the n, then df1 dx is equal to nx to the n minus 1. If you want a nice proof of that, I can give you a nice proof of that. But actually, before I even do that, I should go into the properties of the derivatives that are important. Let me insert some space. Insert some space. And properties of derivatives. Well, a derivative is a linear operator. Anybody know what that means? A linear operator. It means it has two properties. And the properties to be a linear operator is that if you have f of x, excuse me, if you have f and g, right, then if you apply the derivative to f plus g, what is this equal to? Correct. This is equal to df dx plus dg dx. This is a property, can't be proven. Well, no, you can prove this. You can prove this.
It's just like a distributive property.
Effectively, yes. You can prove this. It's fairly straightforward. There's no need for me to prove this. If you want me to prove this, this is an after-school exercise. Yeah, I may have. And the other, this is the first property of being a linear operator. The second property is that d by dx of CF is equal to, where C is some scalar. Correct. So these are, these are the two properties of a linear operator, very important properties. I mean, clearly you can actually go through and prove almost all of these rules using these properties, referencing them. So, and then there is the product rule. Yeah, I actually did prove this to you guys, for those of you who are taking the C exam. What happens if you have the multiplication of two functions? In other words, you want to find, you have a function f and you have a function g, and you wanted to know what the derivative of f g is. It's not the chain rule, it's the multiplication rule. Correct. So, I wish I could keep this on here. I want to pin you. Thank you. All right, so this, I'm going to grab this. No, I'm not going to grab this. I'm going to grab this and move it here. This is such a killer application. It really is, right? I mean, it blows away the smart app.
Snow days where we have to do this.
Huh?
Like if we have like a snow day or something where we miss school for some reason.
Oh, that'd be so cool.
What do you want to do with this?
Like, will we have to like come online and like
That'd be sick.
I could do it. I mean, that actually.
I'm not saying that you should. I'm asking if you are.
I don't know. Let's see.
I remember last year you said that we should be doing work
On the snow days, what I'll probably end up doing is assigning free response questions. Because the nice thing about you guys is, number one, all of you have had me before. The only person who hasn't is Jonathan. And do you know that for a fact, or?
I can confirm it.
Okay.
I'm pretty sure. He's either homeschool or school.
Okay. So yeah, I mean, and so that means everybody's going to has had me before, which means that I can go and assign past free response questions, and you would actually know how to deal with them. You know. The other thing I want to talk to you guys about real quick before I continue is Science League. I think we could actually be competitive this year for C, which is pretty cool. So.
You think C would be harder? Because you know how the C exam was kind of easier than
Well, I'm looking at it from a competitive standpoint. From a competitive standpoint, they're both going to be really hard because Ridge has they have a dedicated program, and I'm just starting it up. No, we could challenge them this year, and I think what it would entail. I'm the New Jersey Science League co-advisor. So what I'm going to do is, I think on Thursdays I'm going to start having prep for New Jersey Science League, and I think we need 5 people to do it. Well, that's the thing, is I think it's going to be allocated to the people who will put it first. In other words, if you have, let's say, band or some other sport that's directly after school, then you're automatically out. I think unless you've basically told your coach or whatever that this is a priority and you'll take whatever punishment in the sport that you get. I mean, you know the deal. I mean, come on now. So here, this is something that can be proven, and the proof is actually quite interesting. It's something that you should check out. But basically, it is, I guess you would say it's df dx times g plus f times dg dx. And I want you to really pay close attention to this. Notice what I did here. Anybody want to pay very close attention? What did I do here? Correct. In other words, I kept it in its order. And the reason why is although your exposure this year, next couple years, you're going to be dealing with functions that are commutative, it's not generally going to be the case. You may actually deal with, you may be operating on objects that are not commutative. And something that's particularly important when you get to linear algebra or what's called functional analysis. So not many people will be doing this, only the foolish. So, so now we have those properties of the derivative. I guess I should probably give you the chain rule as well. And the chain rule is kind of the, it really is the killer derivative rule. And how would you formulate the chain rule? See if you guys can. Yeah. So if you first you need to be able to express. First, you need to be able to express f of x as what? Correct. So right off the bat, there exists functions f and g. Right? That's the there exists symbol. Such that f of x is equal to f of g of x. Right? That is like where you start off. And then what the chain rule basically says is that df dx is equal to df dg dg dx. And this proof is actually pretty nuanced. You need to actually prove another theorem called Carathéodory theorem, something like that. Somewhat. I mean, I think largely I'm going to stick to the physics, but
you were like root 2's not radical or whatever that was.
Not rational. Oh, at the end of the year, no. The end of the year, I'm going to actually dedicate towards Kerbal.
Woo!
Kerbal Space Program.
Ah.
It is. Well, that doesn't mean I'm not going to be proving things mathematically. That just means that I'm not going to be doing, let's say, like last year I had to introduce a whole series of things to prove things that are fairly straightforward. Like, yeah, small angle theorem. All you guys know this stuff at this point. And so if I do anything, it will be along the lines of vector calc, which you may not necessarily have seen before. Vector calc's calc 3. All right, so but the point I want to really stress this year is the physics, because really, well, I mean, it's not even so much that, but you're going to be learning deeper problem solving with calculus in physics. And you'll be able to tackle classes of problems that you couldn't last year. Like, for instance, the Tarzan swing problem. Or,
Oh, the really hard one?
yeah, it's hard. Or,
Did you find it?
yeah, I solved that one. But it's like, that would be an extreme. Or the maximal distance problem is one of the first problems that you're going to be learning in kinematic, or when we do kinematics. In other words, what angle would you fire something in order for it to be moving away from you at all points in time? In other words, there is an angle such that if you shoot a projectile, its distance from you is always increasing.
No matter what speed you shoot it at?
No matter what speed you shoot it at. It's like think about what would be a counterexample of an angle where the distance is not increasing at all times. Yeah, straight up or like at some type of high angle. You shoot it, right? It's moving further and further and further away, and then it starts getting closer to you at some points, right? But there's going to be an angle where it's always moving away from you.
What do you mean, like even after it hits the liquid?
At all points in its trajectory, it's always moving away.
Like there is no ground, like no circular motion.
Yeah, there's a ground. You're projecting this onto the ground.
Well, then if you just shot it like straight forward, like I don't get it.
You'll see. You'll see. We'll get there. But right now, let's focus on, we're going to be focusing on E and M. So other functions. What are your other functions that you're going to be interested in? Oh, by the way, this is only true for what n? For what n is this not true? Be careful. Be careful. It's not true for, oh no, this is always true, of course. I'm thinking of integration. So, F2. So, if F2 is sine, the derivative is? It's cosine. F3. Notice, why am I actually doing this? As opposed to just keep on saying fx, f of x. So this way you know these are distinct different quantities. Cosine x, negative sine. And you should prove all of these. I can't stress this enough. You should go through and prove all these. It's a great exercise using the definition of the derivative. Tangent, I think, is another one that we're going to use. It's secant squared. Or 1 over, I'd rather use 1 over cosine squared. Don't worry about those. Those, I mean, you can use those, but I'd recommend doing the chain rule. These are the ones that you're going to hit a lot. And we're going to be hitting them like first right in this unit. And then there's the really important ones. ln, f6, e to the x. These are not so easy to prove. You have to actually go through and first define E. I don't know if I did this with Kendall last year. Oh, maybe I did.
I definitely remember going through the whole series with E.
Yeah, and it's
Wait, is it the derivative of e to the x, e to the x?
correct.
Nice.
So that's good. I mean, it's good that you guys know these things. I think that's it. I don't think there's any more. Yeah, 1, 2, 3, 4, 5, 6. That's basically it. You got the chain rule. And now let's deal with integration. So you're going to use log, right? So no. Everything, in general, you're going to always want to re-express any logarithmic function as a natural log. And why would you do that? Correct. In other words, when you're going and you're doing any type of integration or operations with these things, it's easier to go back to the function whose derivative is itself versus the derivative of itself times some constant. So, no, we're just going straight to lessons. In fact, we're not going to be doing a formal E&M lab until we get to potential, because there's no. This is all pretty heavy theory stuff, because this is.
Go through this really quickly.
I don't think it's going to be very quickly. I think I've scheduled this for 18 school days. So this unit's like, yeah, it's almost the entire month. So we're going to go at a nice pace as opposed to what I did last year, which was very too fast. No, meaning like last year APC.
And you said E&M was the one thing that you failed your students on last year, right?
Yeah, and that's because I put it second.
Yeah.
So
How did they do in the United
they did fine. Only 2 people didn't pass. But really, it should be pretty easy to get 5s on it.
What didn't pass?
2. So now integration. How would you define the integral? I mean, this is not so easy. Okay, well, the area under the curve. So we should start with the area under a curve. But what does that mean? So then what's the area under a curve? So first, let's actually draw it, right? Here's f of x, right? And what are you doing here? All right, so that means you're evaluating this f, right, at some point in an interval, right? So let's suppose this is the ith interval, which means that this is indexed as xi minus 1. This is xi. And what is the area of that box or that rectangle? Be careful. What's the area of this rectangle? There is some point in between xi minus 1 and xi, right? Where you're evaluating this function. Right? And I'll call this xi star. And so what's that area? What is it? Be careful. This corresponds to, this is xi star, right? It's f of xi star times the width, which is, that's right. Now, one of the things I didn't tell you guys about last year, which I'm doing this year, so if I wanted to actually find the area of all these boxes, what would I do? I'd do a sum. And how many boxes are, how many rectangles are there going to be? Be careful. How many are there going to be? N. That's right. So I equals 1 to n. So right there, and then how would I actually get the area under the curve? What will I have to do? I'd have to minimize the width of the rectangles. What is that? What are you doing by minimizing the length? That's right. You increase, right? You have a fixed bounds. So let's say this is your x0, this is your xn, right? So those are fixed. In other words, that length is fixed. So if you jack up the number of partitions, what is that going to do? Make them thinner and thinner. That's right. So then we could say that the area is equal to the limit as n goes to infinity of x of I star times xi minus xi minus 1. Right. You need the sum. Get over here. Actually, you know what? What happened? All right. Nice. So what I can do is I can first insert space. Okay. Go back up. And now I'm going to lasso this. Move it down here. Right? And then, oh wait. So then I'm going to put the limit here. So it's going to be the limit as n goes to infinity. And that's equal to the area. So now, but the question is how does that relate to derivatives?
If you take the integral, the derivative of the integral is
Yeah, but I'm asking you a different question. I'm asking, like, what does this relate to derivatives?
Like you have a variable balance, then it's the actual.
So now in order to understand how this relates, what you do is we're going to graph a different function. We're going to graph a function whose derivative is little f of x. So we graph this other function. So here is this. So we're going to graph some other function. And this is f x. Notice this is capital F. And little f is equal to df dx. In other words, this is a given that little f, that this function big F has a derivative of little f. So here's this function of big F. Okay? So you take 2 points. How about we take those 2 points that we just showed earlier? xi minus 1 and xi. Right? So now there's going to be a point such that what is true? There's going to be a point in between here. Let's take, I think it's about this point, such that what is true? The slope of the tangent line is equal to the slope of the secant line of the interval. Anybody know what that's called? That's right. That's the mean value theorem. So what does that mean? What does that mean?
Oh, are those spots the same?
Wait. Let's see. What does this mean?
That the derivative at that point.
That means that, let's call this point, I don't know. Let's call it x bar I. Let's call it x bar I. Okay?
Is it just the mean slope graph?
So what we know is that df dx at what point? X bar I is equal to what? What's the slope of the secant? That's right. Very nice. But what's df dx? Huh? That's little f. So this is little f at xi bar. And this is equal to right? So now what do we have? Let's rearrange this. What we have is then that f of xi minus f of xi minus 1 is equal to but that should look familiar to you guys. What does that look like?
That's the area.
That is the area, or that is similar to the area of that under that summation.
Wait, that's weird. So the
Right? So what happens as we start letting n go to infinity? As n goes to infinity, f of xi star approaches f of x bar I. That is called sequential continuity. In other words, you have the sequence of points, and it looks just like another sequence of points along the same exact...
Wait, Mr. Khalil, so does that mean that if you have like an acceleration graph, like a versus
t,
and you look at a time frame at does that mean that the change in acceleration is equal to
the change in velocity is equal to the area under an acceleration time graph. Correct.
Well, I'm looking at this left side right now.
Yeah, you'll see shortly. So what does this mean? What this means is then we have that the sum of f of xi minus f of xi minus 1, right, from I equals 1 to n, limit, you don't even need the limit at this point. It's kind of implied that you're shrinking these intervals, is equal to this sum. But what's the beauty of this? Let's see if you guys can identify what the beauty is. Give you a second to talk about it. On the right-hand side, can we evaluate that sum? And the answer is not really, not easily. Right? We have to know the function at each of those points. But what about the left-hand side? Why? What is that? This is called something. And if you want, we can evaluate a few terms. You'll see exactly what happens. Right? The first I is going to be I equals 1, right? So this is f of x1 minus f of x 0. What's the next term in the sum? That's right. That's right. Right? Plus all the way out to the nth one, which is and so what we end up with is that sum, which is the area under the curve, is equal to what? The final f at xn, right, minus f of x0. That is the area under the curve. Right? But what is big F called? Big F is the function whose derivative is little f. In other words, big F is called the antiderivative. Antiderivative. Did you guys go over this in your calc class?
You went over it with
No. Did you go over this? Did you do this in your calc class? Okay, so it's important that you understand the theory because as you can see, there's a whole little bunch of nuanced assumptions that go into this. They're not obvious. You have one sequence that's approaching another sequence, and it's like, oh, that's interesting.
That's why when doing an integral, you can just take the first and the
Upper bound and the lower bound.
I never really understood why.
Exactly. In other words, the reason why is because the antiderivative telescopes. So, there you have it. So now we need to actually be able to, but notice, anti-differentiation or integration is the way I kind of compartmentalize in my brain is that multiplying polynomials is to factoring what derivatives are to integration. In other words, if I take two polynomials and multiply them, right? X plus y times x squared plus y squared, right? Is that an easy or difficult operation? It's relatively easy, right? In other words, there's just some straight up rule called the distributive property that you just follow sequentially over and over again. You add up all the like terms, which is just reusing the distributive property, and lo and behold, what you end up with makes perfect sense. Factoring, on the other hand, right? Factoring requires real skill. And you probably don't think it does, right? You probably think that factoring in your mind is probably similar to multiplying polynomials. But just to give you an idea that, no, actually factoring requires skill, consider this. If I were to ask you to factor the following, how would you do it? This is not an easy factoring problem. This is not an easy factoring problem. Here's another one. Right? Factor that. Yeah. No. This is like you need to go through a series of really sophisticated techniques to actually find the factorization of that. So, in the same way, right, differentiation is a pretty easy operation, right? But integration requires real skill. Exactly. Like differentiation, you just apply the same set of operations or rules over and over again. But integration, there's several chapters dedicated to it in calculus. In general, I'm not going to actually go through those. The way I do integration is kind of like holistically. And you'll see, I use substitution very, very frequently, even in times where it doesn't belong. So, but let's go over the basic integrals. So your basic integrals. Well, I mean, clearly there's going to be the integral of f of the integral of x to the n dx. And for those of you guys who haven't seen this before, integration always requires that dx. Why? Because what does this thing correspond to? That's right. This is your function, right? This is your f of x, right? And what does the dx correspond to? Yeah, your delta x. You're each one of those increments that you're finding f of x at. So this is your delta x. So it's important just to keep this in mind. Of course, that integral sign is a sum. That's actually why it looks like that. It's supposed to be an S. That's Leibniz notation. So x to the n dx, the integral of x to the n dx is? That's right, x to the n plus 1 over n plus 1. Is anybody here who's not taking calc this year? Just you. Awesome. Fantastic.
But you haven't taken calc.
Jonah, he is objecting in principle. So, and you'll see, it won't make any difference. And then there's other ones. Then there's, you easier one to go through is cosine. Integral of cosine x dx is? What is it? Wait, what is it? All right, so how do you know this? But let me actually, I made a mistake here. I made a critical mistake. Anybody know what it is? Okay, so I reject the whole plus c. Okay? And the reason I reject it is because guess what? We're always going to be dealing with definite integrals. So I'll probably put a, b. A to b. And before I even go into any more, what does this mean? What does that right side equal? So in other words, this is going to be b to the m plus 1 over m plus 1 minus a to the m plus 1 over m plus 1. And so I'm gonna be explicitly saying this, because I don't think there's a single case where we deal with an indefinite integral. So likewise, integral of cosine x dx is equal to, from a to b, is equal to the sine of b minus the sine of a. And let me actually go 2 steps ahead or 1 step behind. It's the sine of x from a to b, which is equal to the sine of b minus the sine of a. So who didn't have calc last year? 1, 2, 3, 4. You didn't have it either? You did. Who did not have it? Okay. So
That's like a. It's definitely like an equation. Right?
for which one?
Sine b minus sine a.
Yeah, you'll see. It's like it's not exactly an equation, but no. Well, you're thinking of something, and I know what you're thinking about, but you're missing a couple terms. Integral of sine of x is going to be negative cosine. All right, which is equal to negative cosine b minus cosine a. And then there's what? There's the integral of 1 over x, dx over x, a to b, which is ln of x, which is equal to a to b, ln of b minus ln of a. And then, of course, there's e to the x dx, a to b, which is e to the x, a to b, which is e to the b minus e to the a. Yes? You can, and we will. But I'm not going to, in general, I want to draw out these steps because the people who haven't had calc, this is a lot to kind of internalize. We'll get there. Anything else I'm missing, guys, as your major ones? All right, so now these are new things that you've never seen before. So now no one here has seen this. Actually, that's not necessarily true. So line, area, volume. Okay? So everything we've done, or everything I just showed you, line, area, volume. We're going to go through each.
I thought you said the line has area and volume.
No.
I'm really confused.
So with regards to a line, how many dimensions is a line? 1. So the line is 1 dimension. And in fact, everything we've done, or everything I showed you, is calc in one dimension. So, for instance, if I were to ask you a line,
Well, you can't really.
It's only like the x-axis. It's not x.
yeah, it's not x and y.
No, I'm not talking about a line. I'm talking about the calc that we just worked with.
Because generally speaking, the increment, and this is exactly a good question, the increment that you're dealing with is only in one dimension. So in other words, in the case of a line, your increment is dx, dy, right, or dz, or dr. Yeah, in other words, you're only going to be incrementing over a specific, like, over one. You're only going to be incrementing f over the x, instead of x and y. All right. This is line. And in general, if you have something continuous along a line, that has something called a linear density. So linear density, usually denoted by lambda. And linear density, if it's linear mass density, what is the relationship between lambda, m, and any one of those parameters? Say dx. That's right. Now it equals, be careful. What is density? Increment of mass, right, divided by whatever our parameter is. In this case, this is linear. So this would be increment of mass over the increment of length, exactly. So lambda would equal dm dx, or dm dr, or dm dy. Similarly, if we're dealing with linear charge density, correct. Linear charge density, what would linear charge density correspond to? Lambda equals dq dx. And I'm going to erase the rest of these so that you understand that we're only dealing with one parameter. It's only one parameter, dx, or dy, or dr. And in general, the physics that we're going to be studying is almost exclusively one parameter. But I'm going to be doing stuff that deals with more than one dimension, so that you see what the next level's like. But generally speaking, you're only going to be operating in one dimension. So, 2 dimensions. What does 2 dimensions look like? Or area. So, your dA, your areal element, is going to be what?
Wait, I have a question. Would it, like, you remember the thing? It was like fire, and then you play music, and like.
Yes.
Would, like, if you were evaluating like the height at all those points, would that be like an example?
That'd be a great example. So your height. Does everybody know what he's talking about? Yeah. It was called a pyro board. Remember the Rubens tube that I showed you guys, like a video of you to you guys? Maybe not everyone. Are you sure you remember this? Here.
No, it was like it was a fire. It was a square thing where you play music and it flames. But we never did the play. Yeah, I know. Well, I had the last two. Did we really? Yeah, we. I mean, clearly you had the last.
So this is what Zach's talking about. And it's a really great example, Zach.
Yeah, go for it.
Okay?
Whoa!
So as you can see, the height of this flame is going to be your function. And that function is going to be evaluated
You've seen a Rubens tube before.
at
That's
every
basically a pipe
aerial
with a bunch of
element.
holes in it, and you pump in a flammable gas and
So-
light it on fire. So you basically create a row of Bunsen burners. What's
What?
really cool is to play some sounds into
Yes,
the
I do.
tube, and you can actually set up
It's really good
standing
stuff.
waves. That
It's
is,
like this would
there
be
are
what a
areas, there are
line
patterns
looks
of the
like, where
vibration of the
the height
air,
of the flame,
where there's a lot of vibration
right, is
in
gonna
some
be a
parts
function
and not
of
very much
X.
vibration in other parts. Now that affects the
right?
flow
This
rate
is a
of the gas
one-dimensional
inside that
linear
tube
function. Or,
into
excuse me, this
the
is a one-dimensional
atmosphere, and so it
function
affects the
over a
height of
line.
those flames. So basically, you can visualize the standing wave pattern. I'm currently in Denmark with a team of physics and chemistry demonstrators who have taken this
Which,
experiment
by the
to the
way,
next level. They've actually created a
I've got
two-dimensional
a whole.
Rubens tube,
Oh
a
man,
whole
it's so.
plane
But unfortunately,
of
it's not for
Bunsen
this
burners,
class.
effectively. How many holes
Oh.
2,500.
2,500.
It's for AP1.
Board. So we're going to see 2,500 little flame.
Like getting an entertainment from Verizon saying we can't turn it.
Yeah, right. Yeah. So let's hold off, because that's a long time away. So then, what would this correspond to? An aerial element would correspond to a little square, right? So Okay, so an aerial element would correspond to a little square. And that little square is going to have what infinitesimal dimensions? dy by dx. dx by dy. And so dA would equal what? dx dy, right? But unlike one dimension, it depends upon what coordinate system you're using. So for instance, what would an aerial element look like in polar coordinates? Is it dr d theta? It's not. So let's take a look. Unlike a one dimension, when you actually deal with an area, it depends upon what coordinate system you're using. Right? So now in Cartesian, it's just going to be this. So what you could do is you could morph this. So first and this is in Cartesian. In polar coordinates, although what I'm saying is not technically correct, I should actually go and do a slight adjustment for one dimensions. But there's no need really. So what I'll do is I'll take dA, and I'm going to take this, I'm going to morph it a little bit. In order to understand how I'm going to morph it, first I have to set my origin, because the origin is very important in polar coordinates. So I set my origin. Here's my origin. So now where's my aerial element going to be? It's going to be some point in that space beyond the origin, right? So I go and I take this box and I morph it like this. Correct. So, this little aerial element, dA, is located how far away from the origin? R. It's located R away from the origin. This is not curved. This is curved. This is not curved. The two sides aren't curved. So now, what are the dimensions of this box? Well, let's go with the easy one. Let me actually exaggerate this a little bit more so you guys really understand what's... Right? So that's R away. What is this increment? What is that? Very good. This is dr. This is the increment in the radial direction. What is this? Be careful. Very good. In other words, this angle is d theta, and this length is the arc length, which is r d theta. So your aerial element in polar coordinates is going to be what? R dr d theta. Does this make sense? Why? Explain why this makes sense. What I'm asking you is integrate this for a full loop. So you integrate this over a full loop. What do you get? What does theta extend to for a full loop? 2 pi, right? So you extend it from 0 to 2 pi. What's the integral of d theta? No. Theta. The integral of d theta is theta because the function in front of it is 1. Right? So theta going from 0 to 2 pi equals 2 pi. Right? So now let's integrate r dr. R squared over 2. And you get pi r squared, which is area of a circle. So it makes sense. All right. So there you go. That's polar coordinates for area. Now we have to deal with volume. Good.
You say with the one dimension, that's a line. But a line is simply seen as like when drawing a line on a graph, it's having 2 dimensions, your x and your y. And then this. Why is it well, like, if we have 2 different values. And then this is you have your y and x, and then you have height.
Correct. Well, not necessarily. You're having some surface. It would be more like a surface.
So what would the next level be added?
Next would be a volume. All right, so I understand what you're saying. What Jake is saying, no. Be careful. That function is the surface. Like if I go and play you that again, right? That is going to be a surface area that changes over time. If I take a snapshot of that thing,
It's just the surface area instead of the board and the height.
correct. So let me go back and play this again.
Of the air.
All right, so this, if I freeze this, right? Now this is frozen in time. What that is describing is that surface at that fixed time. And notice that surface, what that surface is, depends upon where you are in space and what period of time you stop the stopwatch at. So then what would be the next one? The next one would be a volume expansion. Where the volume's transforming, exactly. Well, you'll see. The volume is next, and I'm actually just gonna create a new sheet. Oh wait, I need to go back and do one more thing with surface. So similarly to linear, there is a symbol for surface, and surface is sigma, lowercase sigma. So like for instance, this would be surface mass density. So what do you think the surface mass density would equal? Let's see. Surface mass density. Well, it would be whatever that quantity that you're dealing with is, which is m. So you're going to have dm. And the denominator is going to be, or dA. Likewise, surface charge density. Let me take this, because I don't want to write this again. too bad. Surface charge density would be what? That's right. Is dq dA. So now we go to volume. All right. So volume. Okay. Now clearly, volume, we have even more choices. Because there's two different types of, there's three different coordinate systems we could use. First one's obvious. Cartesian. And what would that look like? That's right. It would look like a cube dv is equal to dx, dy, dz. And that would just look like your straight up cube. And this would be dx, dy, and no, that's dz. And the thing that's a little bit annoying is that once you start moving to 3 dimensions, it becomes a little difficult to specify what you're going to call x and what you're going to call y. So like, for instance, I think this should probably be x and that should be probably y. So I'm going to erase that. So this is going to be dx, this is dy, and height's dz. So Cartesian's easy. So there's two types of rotation or of polar coordinates in 3 dimensions. One is called cylindrical, and the other is called spherical. Let's deal with cylindrical first. So cylindrical coordinates, and you guys have already kind of dealt with this on some level. Spherical is the only one that's totally new. So for cylindrical coordinates, what do we have? We're going to form the same aerial element as before. So you have your origin. So you have your origin. Right? Now, this side is going to be dr. And realize what I'm doing is I'm morphing the cube. I'm morphing that cube to be the same dimension or the same volume in this new coordinate system. What's this length? RD theta. So then what's missing? Or dz. That's right. So I give it a height. And there you go. So actually, cylindrical coordinates is very easy. This is dz. So dv is equal to r dr d theta dz. That's nice and easy. Now we go to spherical coordinates. And this is not easy. You know? In fact, I didn't even have time to write this down. But I'll wing it like I normally do. So, see if I can remember how to do spherical. In order to do spherical coordinates, I need a sphere. So let me see if I can find a sphere. I do, but it's not a very good sphere. Oh, perfect. That's right. Oh, this is actually a killer new toy that I got. It's a timing ball.
Oh, that's cool.
Here.
That's so cool. That would make
Right, so I go and I have this wall, right? Oh, that's T. Okay, and then I go and I... Oh, nope, didn't work.
Wait, it's hard though? Does it break?
No, it's actually quite... So.
It's like,
I was expecting that.
it starts it when it starts accelerating, like it has to accelerate.
See, this is not cool. It doesn't work as well as you'd like it to. So anyhow, going back here. So what I'm going to do is I'm going to actually take a point on here. So spherical coordinates is exactly the coordinate system that's used to specify a place on Earth. And how would you specify a location on Earth? And what is a latitude and longitude line?
Oh, it's
Yeah, so then be careful. Very good. It's a measure of angles. Your latitude and longitudinal lines are two different angles. And then the third measure would be R, right, elevation, but in the case of the Earth or some ball, it's going to be your radii. So if you take a radius and you were to swoop it around like this, right, you get a disk, right? And then if you take that and you swoop it like this, you'd get, be careful, you take some R, right? Swoop it around. What do you get? You get a disk. I take this disk and I rotate it 180 degrees. I take the disk and I rotate that like that. You get a, be careful, you get a sphere. You get a full sphere, right? Oh, is that me? Sweet. I think I did book it.
Yeah, you did. Did you need them? Because I get them back for my later classes.
If you want, you can take it.
Can I take it for today?
Yeah, go ahead.
No, we don't do it wrong.
What'd you say? Oh, no. In general, like, I think the only class I would need it for is next block, but I don't even think I need it next block.
Because I need it next block.
Take it next block. Go ahead. Yeah, absolutely. No, don't worry about it, man. That's what this class is for. We are disturbed to begin with. So, huh? Yeah. So, Chem. So, if you take this, right, and just start flipping it. Start flipping it. What's going to end up happening?
That's not angle that you said before, right?
No, it's just flat. You take this flat thing, right, and you rotate it by 180 degrees, you get a sphere, right? Because this is going to fill in this, this is going to fill in this, and this is going to fill in the top. So you need two independent angles. So let's actually go through and figure this out. So what's going to happen? So your volume element is going to look like this. First you have your origin, and then this is going to be rotated. This is a little hard to draw. Let's deal with, there's R. This is our dr. This, first, what do you want to call this angle? Be careful. Let's call this phi. Let's call this theta. Okay? So then this is going to correspond to the change in phi. So therefore, this is going to be r d phi. Now, how's d theta going to go? D theta is going to be like this. So this is extremely difficult to draw.
Oh, so that's coming out of the board.
This is coming.
Okay, so right now what we're looking at the board is.
I see what you're doing.
So this, if you take a look at this corresponds to, wait, that is your d phi. This angle is d phi. So now, the part that's going to be rotated in a circle is this. That's your theta. That's going to, so this is going to be your d theta. So now, but the problem with this is we have to figure out what distance is actually going to be wrapped around. Here, I'm gonna have to actually redraw this. So here's my origin. This is okay.
So that's your DR and your RDT, right?
Correct. This is your R. Okay. Now this thing, so this is going to be R d phi. This is d phi. And now this chunk is going to be wrapped around. So this, oh, how do you do this? Into the board is going to be your d theta.
Yeah.
Right? So now that increment, because it looks like this.
I see where you're going.
So what it looks like is this.
So the way it is turned around the pole, right?
So here's your d theta. But now the question is, what's that radius? What is that radius? Be careful. That radius, because that is the radius with which it is actually sweeping around. Because what you're going to end up with is something that looks like this. Right? If you're looking at it in terms of if you sweep it around a full 360 degrees. Now, it's effectively infinitesimally thin. So in other words, this is going to be your dr d phi. So
Wait, can we have it where, like the things like this?
well, this length right here, this is r. This is phi. So then, what is this length? R sine phi. And so then what we have is that the volume element, the volume element is going to be R sine phi d phi. Wait, I'm sorry, that's d theta. Sorry. R sine phi d theta, because this thing is d theta, and it's r sine phi is the radius with which you're rotating it, times r d phi dr. So then your volume element, dv, is equal to r squared sine phi dr d theta d phi. Yeah, it's a little nastier. And with that, are we done? Or no? If you're integrating over something that's a sphere or a hemisphere, you might want to use spherical coordinates. Each one of those has their advantages given the type of shape. Later. I will see you guys what? Oh, wait, guys, I need you to do me a favor. go on WebAssign, okay, and take the WebAssign test.
I did that.
You did it.
Yeah, it was like 1M plus 1M is 2M, and you put it in, you say check, and I'm like, okay.
All right, that's all you have to do. And it's just like 1 plus 1 equals 2.
Yeah.
And it's just to verify that everyone, that it works.
I was like worried, I'm like, you stop.
Yeah, well, it'll tell you.
You should probably drop the class at that point.
Yeah, right?